This is our the third talk of the morning, and we have Yasuko Takei from the University of Tokyo and ERI. We'll be talking about constitutive mechanical relations of a partially molten rock in terms of grain boundary continuity. Yasuko.
Okay. I am Yasuko Takei from ERI, University of Tokyo. In this work, I collaborated with Richard Katz and Ben Holzman. Okay. Macroscopic dynamics of partially molten mantle, such as melt segregation and seismic wave propagation, can be treated within the framework of continuum mechanics by using two-phase flow theory. However, mechanical constitutive relations, which specify the point property of the macroscopic system, is determined by the microscopic processes at the grain size scale. So, this problem is a multi-scale problem ranging from micrometer scale to 100 kilometer scale. Ultimate goal of my study is to clarify the effect of the microscopic process on the macroscopic dynamics. For this purpose, I divided the whole problem into two parts. First, I theoretically derived the mechanical constitutive relations based on the microstructural model. The obtained relationship includes contiguity, which represents the grain scale microstructure of partially molten rock. So, in the former part of my talk, I will talk about this theoretical approach and demonstrate how mechanical properties of partially molten rock strongly depends on the contiguity. And experimental studies shows that contiguity is not constant but changes under the deviatoric stress. So, the second part of my talk, in the second part, I will demonstrate the effects of the contiguity change on the macroscopic dynamics by solving the governing equations of two-phase flow theory together with the mechanical constitutive relations, which include contiguity as an internal state variable. Okay, so the first topic is the derivation of mechanical constitutive relations based on the microstructural model. Here, I briefly talk about the time scale of our concern. The time scale of elastic wave propagation is given by the period of the wave. Ultrasonic wave, which is used in the laboratory studies, is 10 to negative 6 or 6 seconds or less, and seismic waves, which is used in seismology, is from 1 to 100 seconds. In contrast, melt segregation is a geological process, and the time scale is longer than 100 years. In the ultrasonic wave, partially molten rock behaves elastically. So, the elementary process at the grain size scale is elastic deformation. In contrast, in melt segregation dynamics, partially molten rock behaves viscously. And as I shown later, the elementary process of the viscous deformation of partially molten rock is diffusive matter transport, which is completely different from elastic deformation. So, depending on the time scale of the mechanical response, governing equations of the grain size scale is completely different. Such multi-time scale behavior is another interesting aspect of this problem. In the seismic wave, both of these processes, elastic deformation and diffusive matter transport, are active, causing dispersion and attenuation of the seismic wave. Such intermediate property between elasticity and viscosity is called unelasticity. And my talk today is focused on the two end members, elasticity and viscosity. And my talk in the third workshop in June is focused on unelasticity. When I started considering this problem 20 years ago, elastic model and viscous model were completely different, which makes it very difficult to integrate the seismological and rheological studies. In the previous elastic models, melt phase was modeled by inclusions contained in a continuum solid phase. By solving the governing equations and boundary conditions of this poroelastic system, the effect of the pore shape on the elastic properties were investigated quantitatively for oblate spheroid model with variable aspect ratio from sphere to very thin films, and for the tube model with variable aspect ratio from circle to triangular shape. However, these shapes were chosen for mathematical simplicity to obtain analytical solution, and so these shapes cannot be directly related to the dihedral angle, which is actually measured in laboratory. Also, these models do not include grain boundaries, which play a significant role in the viscous deformation of rock. So, these models cannot be further extended to the viscous model. In contrast, previous viscous model is based on the realistic geometry. This is a CK model, Cooper-Kohlstedt model of grain boundary diffusion creep. In this creep mechanism, unlike the elastic deformation, each grain can change shape because material near the grain boundaries normal to the direction of compression moves to the boundary normal to the direction of tension by diffusion through the grain boundary where diffusivity is higher than grain inside. In this creep is significantly enhanced by melt because melt has much higher diffusivity than grain boundary, and also because melt cannot sustain shear stress inside the grain increases. The CK model evaluated this effect simply by geometrical effect like this, without solving governing equations nor boundary conditions. Such simple formulation may be enough for viscosity, but not enough for elasticity. So, this model cannot be further extended to elastic model. So, I developed a granular model which consists of the solid grains making a framework through grain-to-grain contacts and interstitial melt phase. The macroscopic constitutive relations between macroscopic stress and strain were obtained by solving the governing equations of each grain deformation like this. And for the elastic model, elastic governing equations were solved. And for the viscous model, diffusion equation was solved. And as a result, elastic constitutive relation was obtained in a consistent form with poroelastic theory like this, and viscous constitutive relation was obtained in a consistent form with two-phase flow theory like this. And this elastic compliance tensor and viscous compliance tensor were obtained in an analytical form like this as a function of microstructure. So next, I will summarize the remarkable points of these results. First of all, it was found that the essential geometric factor determining the bulk mechanical properties is contiguity, which is defined by the area of grain-to-grain contact faces relative to the total surface area of each grain, like this. Contiguities generally decreases as melt fraction increases. And contiguity 1 means melt-free aggregate, and contiguity 0 means disaggregation of granular material. When microstructure is texturally equilibrated to minimize the surface energy of the system, contiguity is determined as a function, uniquely determined as a function of melt fraction and dihedral angle. This figure shows this relationship for a typical dihedral angle of partially molten rock. Red curves show the model results, and the blue curve shows the empirical relationship obtained from the actually measured contiguity for olivine basalt system. And this figure, this figure shows the results of elasticity and viscosity as a function of contiguity. The estimate of melt fraction by assuming dihedral angle 30 degrees is shown on the upper side. Green and yellow line show bulk and shear moduli of the skeleton normalized to each modulus of the solid phase. And blue and red lines show bulk and shear viscosity normalized to the shear viscosity of the melt-free aggregate. So the first conclusion is both elasticity and viscosity are determined by contiguity. And in this log-log plot, slope is about 1/2 for elasticity, but 2 for viscosity. So viscosity is much more sensitive to contiguity than elasticity. This is the second conclusion. And another remarkable observation of this result is that as contiguity approaches 1, elasticity normalized to the solid elasticity approaches 1, which is quite reasonable. But such reasonable behavior was not observed for viscosity. This is an enlarged drawing near contiguity 1. Shear viscosity is about a factor of 5 smaller than melt-free viscosity until a very small amount of melt, and suddenly increases to 1. Bulk viscosity also shows a similar behavior and suddenly increases to infinite at the end. Such singular behavior of viscosity is explained by this drawing. Without melt, atoms have to diffuse through the grain boundary all the way from the direction of compression to the direction of tension. But with melt, connected network of melt significantly decrease the diffusion path through along the grain boundary, and atom diffusion is significantly enhanced by melt. And such connected network of melt exists even at a very small amount of melt. So the third conclusion is even a small amount of melt can significantly reduce the viscosities. Now I compare the present results with the previous results of viscosities, which are shown by broken lines. CK model does not take into account the network effect of melt, so it does not have singularity at contiguity 1. And commonly used model of bulk viscosity is given by 1 over melt fraction. And this is much higher than the present result. So the final conclusion is that shear viscosity is a factor of 5 and bulk viscosity is 2 to 3 orders of magnitude smaller than commonly used models. So in summary, the present results of viscosity obtained by solving the diffusion equation is largely different from the result of elasticity and the previous results of viscosity obtained from the different elementary processes. So this means that the elementary process at the microscopic scale has a significant effect on the constitutive relation. And so whatever mathematical method is used, like homogenization or effective medium theory, microscopic process, elementary process of rock deformation has to be formulated correctly. At the end of the first topic, I will briefly show the comparison between theory and experiment. In this figure, shear modulus versus melt fraction obtained from the contiguity model is compared with the ultrasonic data measured for the partially molten rock and partially molten rock analog. And also, shear viscosity versus melt fraction obtained from the contiguity model is compared with the experimental data of grain boundary diffusion clip obtained for the partially molten rock analog. Theory and experiment agree very well. But about this jump, experimental data have large uncertainty, and so it has not yet confirmed from the experiment. And this jump, if this jump exists, it has a lot of geological, geophysical implications because very small amount of melt is very important in the mantle. And so recently, John Lach is intensively reconsidering this point of the theory, and our understanding of this jump might change in near future.
Just a quick question. So, zero is a measured viscosity of a dry sample?
Yeah. Theoretically, this is melt-free aggregate, and experimentally, this is very difficult. And with some assumptions, we have to estimate this. So
you don't have a data point for zero melt fraction?
Yeah, because we have, but to obtain the zero melt fraction, we use some very pure sample or something.
So there is a
there is
dot
a data
up
point.
at the left, upper left corner.
Yes, there is, but I forgot one. Yeah, there is a data point. Yeah, but a lot of error in the interpretation. Okay, but this steep reduction of viscosity by melt fraction has been confirmed from a lot of data, experimental data. And in the laboratory, this slope is empirically represented by this exponential function and is called porosity weakening viscosity. And in the second part of my talk, this porosity weakening viscosity is plays an essential role. Okay, let's move on to the second topic. In the second topic, we consider the effect of grain scale process on macroscopic dynamics. As macroscopic dynamics, we consider melt localization instability. And this second part is closely related to the David Kolstedt second talk yesterday. In 1989, by using the two-phase flow theory developed by Mackenzie, Stevenson showed that in the partially molten rock undergoing deformation, homogeneous melt distribution becomes unstable and localizes into channels. This theoretical prediction, although this theoretical prediction had large impact on the study of melt migration dynamics, but detailed form and mechanism of channels remain unsolved. And one of the difficulties of this problem seems to come from the large effects of microstructural processes which are poorly understood yet. So, in my talk, I will review the present state of understanding of this problem based on our recent paper published in 2015. And the purpose of this paper is in the understanding of the mechanism of instability. So my talk is also focused on the intuitive understanding. I first talk about theory of Stevenson. Here, to avoid confusion, I briefly note that in the linear stability analysis in this talk, melt viscosity is assumed to be zero for simplicity. This means that melt can flow without melt pressure gradient. Okay. Now we consider Stevenson's theory. Let's consider a homogeneous melt distribution under tension like this. Because of the mechanical equilibrium condition, tensile stress sigma yy is constant along the y direction. Because stress is given by viscosity by strain rate, this condition can be also stated that the product of viscosity and expansion rate is constant along the y direction. Stevenson showed that this situation is unstable by considering a small perturbation in melt fraction like this. Because of the porosity weakening viscosity of the partially molten rock, where porosity increases, viscosity decreases, and vice versa. And because the constant stress condition, where viscosity decreases, expansion rate is enhanced to compensate it. And where expansion rate increased, porosity increases. So, positive feedback occurs and porosity perturbation grows unstably. In this instability mechanism, the porosity weakening viscosity plays an essential role. And another essential factor in this mechanism is tensile stress. To see this, let's consider the same story in the compression field. In this case, porosity increase results in the enhancement of compression rate rather than expansion rate. And compression rate, increase of compression rate has negative effect on porosity. So porosity perturbation depress. So a bounded porosity perturbation under compression is stable. Also, let's consider this story under shear stress. In this case, porosity increase results in the enhancement of shear strain rate, which has no effect on porosity perturbation. So, bounded porosity perturbation is neutral under shear stress. So, in summary, bounded porosity perturbation is unstable in tension, stable in compression, and neutral in shear. So, the mechanism Stevenson proposed can be called tensile instability. Next, I will talk about experimental observations. Holtzman and Kohlstedt and King et al. Deformed the initially uniform partially molten rock under simple shear and under torsion, and observed the formation of melt-rich bands, these stripes in the photo. And the robust observation of these experiments is that the angle of bands to the shear plane is 15 degrees. Although these bands were considered to be formed by the mechanism proposed by Stevenson, the angle of 15 degrees cannot be explained by his mechanism of tensile instability. As shown in this figure, in the simple shear flow, growth rate of tensile instability is maximum at 45 degrees, so that the bands are normal to the maximum tensile direction. Here, the maximum tensile stress is called sigma 3. And when strain increases, the angle becomes larger because bands are rotated by the simple shear flow. So, the angle predicted by Stevenson's theory is 45 degrees or higher. So, the experimental results showed much lower angle than the prediction. If bands are driven by tensile stress, low angle is not favorable, but if bands are driven by shear stress, low angle is favorable. So this experimental data suggests the positive effect of shear stress on the band formation. So far, two types of theories have been proposed to explain the low band angle. And in both models, shear stress plays an essential role. The first one is, in the first one, anisotropic viscosity is taken into account. And in the second one, isotropic nonlinear viscosity is taken into account. So I will talk about these two models. The first one was motivated by microstructural anisotropy observed in the experiments. Without stress, partially molten rock shows isotropic microstructure, but with stress, anisotropy develops such that grain-to-grain contact area decreases in the sigma 3 direction, like this. And this anisotropy strongly correlated with stress rather than strain. So I call this stress-induced anisotropy. the mechanical effects of stress-induced anisotropy can be evaluated quantitatively by using the contiguity model, which I introduced in the first part of my talk. The stress-induced anisotropy is modeled by decreasing the radius of the two contact faces in the x direction. And when contact radius decreases in the x direction, viscosity component in this direction, Cxxxx, significantly decreases. Because this effect is small to the other components, large viscous anisotropy is predicted. And this maximum anisotropy is called saturated anisotropy. So in this new model, we consider viscous, in addition to the porosity weakening viscosity considered by Stevenson, we consider viscous anisotropy, which is produced by stress-induced microstructural anisotropy. Consequences of these rheological properties to the band formation can be investigated by solving the governing equations of two-phase flow theory consisting of mass conservation equation and momentum conservation equation and viscous constitutive relation for the solid matrix. Here, the viscosity tensor of the solid matrixCijkl is given as a function of melt fraction and stress to formulate the porosity weakening viscosity and stress-induced viscous anisotropy. I first show the numerical simulation. Here, the initial condition is uniform porosity of 5% plus white noise perturbation. And we assumed saturated anisotropy. Okay, start. Here, color shows porosity. So for both cases, perturbation grows into melt-rich bands, and the angle of the band is to the shear plane is about 15 degrees. So to understand why viscous anisotropy lowers the band angle, we performed linear stability analysis. In previous studies, x-axis is oriented to simple shear flow and generally oblique to the perturbation. But we found that if x-axis is oriented to perturbation and generally oblique to the simple shear flow, mathematics becomes much simpler and physics becomes much clearer. In this new coordinate system, the mechanical equilibrium conditions in the y and x directions can be immediately related to the tensile instability and shear instability. Here, the right-hand side shows the stress reduced by the porosity weakening viscosity, and the left-hand side shows the compensation by enhanced strain rate.
Yasuko?
Hi.
What's happening at the base state? How do you define the base state?
Base state is this one, simple shear.
So you have a non-zero velocity at the base state.
Yes, non-zero. The simple shear flow in this direction is happening in this zero base state.
And the base melt fraction, is it constant or spatially variable?
Base state melt fraction is uniform. And first order perturbation is the amplitude of melt fraction perturbation. Okay. And the enhanced strain rate, this enhanced expansion rate causes instability. And these viscosity tensors, CIJKL, is written like this, which displays anisotropy caused by base state simple shear flow. The remarkable point is these off-diagonal components, which do not exist in the isotropic system. These off-diagonal components cause the cross terms, and as a result, the perturbation growth of this system is driven by both tensile and shear stresses. So, with viscous anisotropy, both tensile and shear instability occurs. Such non-trivial mechanics in anisotropic two-phase system can be generally understood by the coupling between shear and volumetric components, which does not occur in isotropic system. As shown here, this coupling has two end members. Under shear stress, because compressive stress and tensile stress is equal, if sample is soft in the sigma 3 direction, expansion is larger than contraction. So, matrix volume increases. This end member is called shear stress induced expansion. And under the shear strain, because contraction and expansion is equal, if sample is soft in the sigma 3 direction, tensile stress is smaller than compressive stress. So, matrix pressure increases. This end member is called shear strain induced compression. And which is the closer of these two depends on each individual situation. In the Stephenson theory, shear instability does not occur, but with viscous anisotropy, the shear stress induced expansion occurs at the first order and destabilizes the shear instability. Also, shear stress induced compression occurs at the base state in the simple shear flow, and so the base state tensile stress is significantly smaller, and this significantly stabilizes the tensile instability. So, because of the destabilization of shear instability and stabilization of tensile instability, band angle is significantly lowered. So in the first model, both tensile and shear instability occur. And next, I will briefly talk about the second model. Katz et al. Considered a dislocation clip of partially molten rock, in which strain rate follows the power law with stress exponents larger than 1. In this case, viscosity is written as a function, given as a function of melt fraction and strain rate like this. So, in this new model, in addition to the porosity weakening effect, strain rate weakening effect is considered. And in this scalar strain rate is given by the second invariant of the strain rate. So, both volumetric and shear strain rate contribute to the strain rate weakening effect. This is the important point of this model. And here, the response of deforming two-phase system to the porosity perturbation is shown for the case of Stephenson's theory. Upper part shows a response under the tensile stress, and the lower part shows a response under the shear stress. These two responses are independent each other, but this strain rate enhancement increases the scalar strain rate. So, if strain rate weakening occurs, it weakens the viscosity further, and it enhances the strain rate further. The importance of this second enhancement due to strain rate weakening relative to the first enhancement due to the porosity weakening is evaluated by n-1. And also, the importance of this shear component relative to the volumetric component is evaluated by bulk over shear viscosity. So, if n-1 and bulk over shear viscosity is large enough, this shear component controls the growth of tensile instability. So, in this case, bands becomes significantly lower, so that the driving force is favorable for this component. So, in the second model, although shear instability does not occur, tensile instability affected by shear stress occurs. So far, I talked about models by focusing on the angle of the bands, because angle represents the physics well. However, in this last slide, I compare the model and experimental results by including the other features than the band angle. The low angle bands can be explained well both by power law creep model and anisotropic viscosity model. But in the power law model, large stress exponents is required, which is not consistent with the experimental observation. In contrast, the anisotropic viscosity model is strongly supported by the experimental observation of the base state melt segregation, as shown yesterday by David Kohlstedt's second talk. This melt migration is driven by shear stress gradient in the solid, which is a new driving force predicted by this theory, and it does not exist in the isotropic system. However, this anisotropic viscosity model is subject to relatively large uncertainties because of the uncertainties of microscopic processes. So far, we considered two versions of this model. Static version. In the static version, the amplitude of anisotropy is fixed, and in the dynamic version, amplitude of anisotropy alpha is given as a function of the amplitude of deviatoric stress. And in the static version, in my talk, I only showed the static version. And in the static version, row angle is limited to relatively large alpha. In the dynamic version, row angle occurs for a wider range of alpha, but growth rate becomes smaller compared to the static version. So, the band formation dynamics depends on the detailed behavior of contiguity. However, experimental data are not enough to further constrain this model, and moreover, there are very few models for the evolution of microstructure at the grain size scale. So, the second conclusion is it is important to study the grain scale microstructure change and deviatoric stress. That's all. Thank you very much.
Thank you, Yasuko, for this interesting talk. Could you just go one slide back, please? The base state melt segregation that you cite in support of the anisotropic viscosity, would you not expect a similar behavior with a power law creep isotropic viscosity because the shear stress gradient would also drive melt migration? I don't think I quite understood the difference.
This does not cause base state melt migration. Richard Katz tested with this rheology the base state melt migration, and he could not. He checked that, he confirmed that this does not cause the. And
is it because of the off-diagonal terms that are absent?
Yeah, I can easily explain the mechanism of. Okay, so the base state melt segregation, very typical behavior is up stress gradient, up the shear stress gradient melt flow. That is, and David Kohlstedt shows towards the flow and flow towards the wall because shear stress is higher in the wall. And this is explained by this. We can apply this. So, shear stress-induced expansion occurs, and when there is a shear stress gradient expansion is larger at larger shear stress, so melt goes from small shear stress to large shear stress. Okay. And this doesn't occur in the nonlinear power law creep model.
David?
So, Yasuko, going back to you don't have to go back on your slide, but at the beginning you talked about this large factor of 5 drop with the first addition of a small amount of milk. And I've never understood physically how that can be, because what's important, of course, is the flux, not the rate of diffusion. It's the amount of material you can move through that small tube along the triple junctions. And when the tubes get to be very small, I just don't, it seems strange to me that they can compete with diffusion through the grain boundaries in terms of the flux. Again, it's not the diffusivity that's important, it's the flux that controls the rate of deformation. Right? Does that make any sense? So you have these tiny tubes along triple junctions.
Okay.
And you're trying to say, or you are saying that flux outdoes the flux along the grain that can be delivered by the grain boundary diffusion. So you have this path that comes down, and then, you back up.
Ben's
drawing, yeah. Right, so you want the flux along that melt channel to compete with the flux along the grain boundary.
Yeah.
And that channel is at 0.1% melt is exceedingly small.
Yes.
And yet it has to carry so diffusion along that must be exceedingly fast
That.
for it to be competitive.
Yeah. So あ、どこ行っちゃったかな。So this point is the switch from grain boundary limiting to melt tube diffusion limiting. So at this transition point, the grain boundary diffusion and small tube diffusion is equal.
The diffusion or the flux?
Flux.
I mean, it's the number of atoms that transport, not the rate at which. Am I missing something?
I think you mean the flux are equal at that point.
Yep.
So then the diffusivity in those tiny channels must be very, 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 very large compared to the diffusion in the grain boundary.
Diffusivity is much larger. Yes.
How much larger is it?
But I forgot the number which I used to calculate this.
My question was about your theory. What will it change if you do it with pure shear instead of simple shear?
Which theory?
The one where you try to reproduce the shear
Instability.
instability.
Do you mean what is the difference between pure shear and simple
Yes.
shear?
What will it change if you
Uh-huh.
assume pure shear and not simple shear? Because in experiment, I would say that at some point it's not simple shear anymore.
In linear stability analysis, it's just the very small deformation, so maybe no difference. But in large deformation numerical simulation, it matters, I think. But linear stability analysis may be the same for both, I think.
Your basic idea is that the stress changes the geometry of the melt.
Yes, yes,
So there is a time scale related to that,
yes.
right? Because if the time scale for everything is sufficiently long for it to return to textural equilibrium, this won't happen. Do you have any idea what that time scale is compared to the time scale that we're concerned with?
In this calculation, for simplicity, we just assumed that geometry is just a function of time, function of stress at any time. But in my experiment, at least there was a lot of hysteresis in the wetting, going of wetting and recovering of the grain boundary. Wetting is fast and recover was not so fast. So, yeah, there is time scale, I agree, but from experiment I couldn't.
Because presumably the time scale for the recovery will go either as d squared or as d cubed, because it's going to be either diffusion on the grain boundaries or body diffusion. And that presumably will govern how important this is in, for instance, in the mantle.
Yeah, I will. We have not yet.
Derek?
Yeah, so perhaps related to this question, so you assume the melt viscosity is 0,
Yes.
and shouldn't that be an important factor in influencing this time scale? If you're pushing melt around.
We usually, for the instability problem, the growth rate is maximum at large compaction length. When compaction length is much larger than grain sample size, the growth rate is maximum. So we can assume melt viscosity is not affecting the maximum growth rate, and we just consider about that maximum growth rate, which does not depend on melt viscosity.
So in the model, when you scale up to an aggregate, at the grain scale, it's nonlinear. I'm sorry, it is linear, right? There's a stress exponent of 1. Does that modify the macroscopic behavior? Is the macroscopic behavior still linear?
In this form, it is linear, but we put stress here. This was considered to be a function of stress, so cannot say nonlinear finally.
Okay.
Cannot say linear.
Okay.
We have
So,
to say
yeah.
nonlinear.
The reason I ask is that in the experiments where there is strong segregation, the stress exponent is 2.
Yeah.
But the basic physics here are thinking about diffusion creep. And so if you want to do an experiment and confirm to yourself that it's diffusion creep, you'd say it has to have a stress exponent of 1. So I'm trying to figure out why there is this difference, and the model seems to match the data so well, but
Not yet so well. So I am thinking that we can easily combine the power law creep model and viscous anisotropy model, and that will be more realistic,
Okay.
closer to experimental condition. And I think, yeah, not yet so very well agreement. So
I'm impressed.
I think we should. Maybe Richard Katz will do. Yeah, I think he is considering that. So for both effects, power law effect and.
Okay, why don't we thank Yasuko again?